Welcome everyone to today's CDAC webinar. It's my pleasure to introduce today's speaker, Dr. Deng from the University of Houston. Dr. Deng is an assistant professor with the Robert A. Welsh Endowed Professorship at the Department of Physics and the Texas Center for Superconductivity at the University of Houston. Langzi has done quite a bit of work in studying quantum materials. His early work focused on high thermal conductivity materials, but most recently he's focused on other materials, and in particular is quite interested in quenching high pressure superconductivity at ambient pressure, which he'll tell us about today. He's also worked on a number of topological materials and other materials, and ultimately this work is focused on technological applications. Langzi obtained his degree in physics from the University of Houston, working with Paul Chu there. He's a recipient of the Materials Research Society Outstanding Early Career Researcher Award and the University of Houston President's Circle Award, and he serves on the Scientific Advisory Committee of the University of Houston Quantum Initiative. We're delighted that you're here to tell us about your recent work. And
Sure.
again, it's been a pleasure working with you on various projects over the last few years. So thank you for finally giving a talk.
Thank you. Thanks a lot for Professor Hamley's invitation and also nice introduction. So during the past few years, we really kind of excited on this pressure quench protocol, which the idea is initiated by my PhD supervisor, Paul Chu. So really that's, don't want to take credit from him. And so I also thank really Professor Hamley's group and the different generation of students we were happy to working with and got some really exciting results. And a lot of other collaborators as listed here. So I'm not going to go through one by one. And also thank our funding agencies, especially Ivy recently on the pressure quenched projects. So now let me get started. So there's one nice perspective paper on the approach for room temperature superconductivity. So particularly today, I'm going to focus on high pressure, right? So first go to the high pressure and then find ways to remove it and still maintain those fancy and enhanced properties, and that's the goal. So if you are interested, I'm really encourage you to read these papers, and also welcome your feedbacks on this. So look at I think many of us have different versions of TC versus the ear map. That's the one constructed by Paul Chu and myself. So just looking at the TC increments since the discovery back to 1911 in the early, the 70 years, we do see a very steadily increase, but in a relatively slow rate. So it's almost like 20 Kelvin enhancement in the time frame of 70 years. I was being told by Paul Chu that in those years, if you get only a few degrees enhancement, that's a great deal. So that's very nice time to study superconductor in that respective. So, but also of course, this brought people some confidence challenge that if we're really moving in this rate, when are we going to reach room temperature? So that seems to be a little bit not that hopeful, right? So fortunately, in 1986 and 1987, sorry, the wrong direction, we do see a quantum leap on the TC enhancement. People break the 30 Kelvin limit, and especially the YBCO that break the 77 Kelvin liquid latent temperature. So that really is like gold rush time for a high TC at that time. So it's very exciting. A lot of things condensing in that few years, a lot of interesting stories. So being more recently, by recently I mean the recent 40 years, we see a TC increase of 200 Kelvin. So that's very optimistic, very promising. And the main, of course, after the cuprates, that the hydride start to really play a dominant role here on the high TC record. So high pressure definitely here play a very important role in the TC landscape, right, over the past over 100 years. So starting with the important role of high pressure in superconductivity research. So being a very fundamental tuning parameter, high pressure was able to change basic parameters of interatomic in the material. We started really altering chemistry. So that's a very clean way to adjust the materials. You can tune carrier concentration, shift Fermi level, and even reshape Fermi surface topology. So that really can fundamentally change the materials structure and properties in that regard. And also one of the questions I asked Paul Chu when I was a graduate student here was, what exactly, right? What triggered him to discover the, superconductivity or discover the YBCO? One of the story or one of the reasons he mentioned that's really at the early days he used those chemical pressure, right, to study the 214 material. That's one of the gives us the hint to lead to the discovery of using yttrium to add the chemical pressure that simulate the physical pressure to trigger this breakthrough. So that's this kind of mindset that triggers a lot of exciting discoveries, including that YBCO back to 1987. Also, it's worth to mention that it helped establish this universal inverse parabolic TC relation with carrier concentration that really formed a very important base for the following theory development and the compound discovery. Not to mention the metallization of hydrogen and the high pressure, and also in the most recent years, the breakthrough that have been happening in the hydride materials. So today I want to, at the beginning of this, the first 10 minutes or so of the presentation, I want to focus a little bit more on this so-called TCP relation. And before jumping into that, allow me to quickly show in, just in case for some of us are not familiar with DAC, even though I assume most of us are. So we do have this different type of high pressure cells in the lab. So beryllium clamp cell, I was very proud to brought up here. Doju told me that's one he invented himself back to the 1960s, 70s, even though the pressure range is pretty low, 2 GPa. So that's why one of the reasons nowadays many people focus on DAC instead of clamp cell, but this one still give a lot of, like it's pretty user-friendly and still it's very useful. Let me put it in that way. So definitely, if we want to increase the range of the pressure, we have to move to diamond envy cell. That's the very famous, the multi-type DAC normally can reach 100 GPa, depends on the diamond Q list we use. And here I just showing one of the but it definitely needs more, training and careful, very handy student take care of it. So one of our students was able to put the 4 leads by hand on the 30 by 30 micrometer samples. It's very beautifully put in there. They're not touching each other. So I'm very proud of this. I'm just showing here. And also there's another beryllium copper diamond envy cell that could adapt to our PPMS, so do more measurements under magnetic field and better temperature control. And recently, in one of the experiments, we studied Kagome materials, we're able to reach around 175 GPa. And it's also worth to mention right now, the NV technique has been intensely coupled into the diamond envy cell. That's give another strong aspect of these high pressure studies. So very quickly. So I was back to 2015, I just want to mention also as a memory of Mikhail Aramis, is he was visiting us during that year. And I was just very busy with defending, preparing for my thesis defense. So there's one day, Paul came to holding the cell in his hand saying, I know you're busy, but do you want to test it? This possibly will make a record, right? I said, yes, I do. And I was happy to run some of the measurements using his cell, even though I'm not going to comment the results today, but it was a very interesting experience. So with that experience, I got into doing the magnetization measurements under high pressure. One of the key challenges, imagine putting everything into this squid, where what we're mapped out is not only the tiny small sample, but really everything, including the background of this beryllium copper cell, the gasket, everything. So that really requires a lot of careful background studies. So for that reason, I visit QD headquarters, and they're very supportive and get a lot of insights on really the mechanism of this machine. And that leads to later our paper on breaking the universal pressure relation using this ultra sensitive magnetization measurement technique under high pressure. So that's a very interesting experience. So speaking of this universal TCP relation, I think we are all familiar with. So basically through doping, you can for most of the materials, it forms like dome shape of the TC. So it's well mapped. That's a very nice story. But the other way of looking at it, that also means the TC, if we really trust these rules, that also means the maximum TC is already well defined. That's why normally most of us, if we start to see the TC start to dropping, then for people searching for higher TC, they may want to stop there to save effort, to save time and money. So, but the question is that really true? Like if you see the dome, it's really there's nothing will happen in the like beyond the dome by doping or by high pressure. So that's brought up to the first topic is hold on, I think. Yes, go beyond. Really, is there how to go beyond the dome? So there's a very beautiful work done by Professor Hamley and co-workers back to 2010 on the Bisco triple layer materials. So firstly, up to around 24 GPa, everything's following the traditional TCP relation. That's nothing expected, and we reached the first TC max here around 124, 125 Kelvin. The most exciting thing is after the 24 GPa, they continue to push the pressure, right? And do see that there's another increase of the TC. So that's phenomenal. That's really nothing we expected to happen. So it's keep going, even then saturate at a pressure of around 36 GPa and hit another TC max at this point is around 136 Kelvin. And the mechanism for the second resurgence of the TC is at lower pressure range, the inner layer of the copper oxygen plane is a competing order. When we go to higher pressure, it kind of tune that into a superconducting order that favors the total superconductivity. So that's very nice picture and also very beautiful results. So triggered by this, the work we're thinking, is it has to be the only reason that give the second resurgence that's really have to be tuning the inner layer. So one of the easy, well, relatively easy measurement, even that saying that's a lot of effort, is we go back to the single layer BISCO 2201. If the only reason is that we have to have this outer layer, inner layer sandwich model, then we should not expect to see another TC resurgence, even though we wish, right? So we do study this material and we keep pushing the pressure up. So surprisingly, for the single layer BISCO, we also see a TC increase after passing the first peak, the dome peak, right? So the numbers here indicating the sequence of this experiment. So like we add pressure all the way to line, everything following the right line, that's the traditional TCP relation, whilst deviates starting from the 10 here, it goes up instead of dropping down. So we do see a hysteresis loop here. So it seems that for the single layer BISCO 2201, it also has this interesting phenomenon that the TC can keep increasing beyond the first dome. Then we move on to the second layer, the double layer BISCO 2212. We sort of see the similar behavior, even though the first range is decreasing instead of increasing, and also later the TC didn't hit up too high. But it do shows that for all these single layer, double layer, triple layer BISCOs, you all have a TC resurgence region and have pretty similar, even the rate is very similar. 1.5, 1.4 Kelvin per GPa. So we would think there must be something universal here that was further explore. At that time, we were trying to collaborate with the serious friend at UTD. So they were calculating the density of states. So that's a well-known way to to look into what's the how the TC got tuned under pressure. So they do find out by calculating the density of states, we do saw a second, right? The second dome appears or a resurgence of the density of states at higher pressure range. And also, interestingly, also shows the indication of the non-hydrostatic condition may play a more positive role here rather than the hydrostatic condition on the second increase of the TC. Of course, this is leads more experimental work or other probes to couple together to get more insights. And but the recently we also kind of trying to revisit this phenomenon by using resistivity measurements, and we come across this very nice paper. Of course, we also catch it once it published. So now we look at this one. So by resistivity probe, it seems that it's more difficult for people to catch the second increase. So basically, including ourselves, we're trying to do the high pressure resistance measurements of this material, but we didn't see the second dome or the second increase appears. Of course, one of the hypotheses here is the high TC part, the second maximum TC, really sensitive to the hydrostatic conditions. So that could be affected by different group using different pressure transmitting medium in the resistivity measurements. So this is still an open question. I just want to point it out here for us. So, but again, it's a very interesting field, and it's worth a lot of effort to find out the truth. So back to this TCP TC years landscape again. So it's a lot of excitement going on. But right now, allow me to remove the pressure. So imagine we don't have the technique to apply pressure to any of the material. So what will be the map looks like? It will look like this, okay? So it turns out the highest TC at ambient pressure still go back to the cuprates, the mercury system, back to 1993, so more than 30 years ago. So that says around 133 Kelvin for the mercury 123 compound. That holds the record so far. So really, so another perspective for us to look into this is we are, through heroic effort, we are breaking the temperature barrier. We are really pushing it towards or even reaching the room temperature. But however, at the same time, we are continuously raising another barrier, which is the pressure. So it's very easy to say, right? It's very impractical for application. On the other hand, it also makes many fully developed techniques that's not inaccessible to to probe this interesting high pressure state, right? Just speak for folks we're doing the high pressure. Normally we're being challenged on, we don't see zero resistance, right? We don't measure this, we don't measure that. But as a fact of fact, it's very difficult, for using those nice tools to under these extreme conditions. So for all this, I think it's time that instead of or in parallel going to higher and higher pressure, it's time to to make a U-turn to look back, to remove this pressure and to find a way to retain these metastable states, still with favorable properties for both science and the technology. So this really brings up to what I mentioned at the beginning. So I think Paul have been talking about this for us and also other colleagues for a while. And just, based on some email record, I do find that it's very specific dates back to February the 2nd, 2019. So there's one sentence code he was mentioning is really worth to look into how to stabilize some of the metastable phase by pressure quenching, right? That basic idea is to really lock in these high pressure properties at ambient conditions. So that sounds too good to be true, but check the history, right? I mean, as Paul Duwas once mentioned, most of the alloys used in industry application are actually metastable, which have fantastic properties. Their counter metastable phases are lacking of, right? So one normally used the example here is the graphite and diamonds, right? So diamonds can form under high temperature, high pressure conditions, and then people are able to very successfully retain that ambient condition, and it's pretty stable, right? So while here the phase diagram may not be, as one colleague pointed out earlier, is not really scientifically correct. The real 3D or 4D phase diagram will be way more complicated. But here we're just trying to show you a concept is by we adding the pressure, we kind of tuning material state from stable to metastable. And in these dynamics, we create such a energy barrier. So one mechanism we're thinking is if this energy barrier is high enough, if we find the correct path or a sweet spot to release the pressure, this barrier could help us to kind of keep this metastable state here, preventing it coming back to its ground state or relatively stable state. So that's based on this, we create this pressure quench protocol, and it consists of 3 stages. I use the colors to kind of distinguish them. So the first stage is really nothing new. That's really the tradition high pressure studies. You apply pressure, you map out the properties as a functional pressure, so step by step. And based on that, we can choose a targeted phase. So speaking for TC, we're really just trying to focus on the maximum TC on the TCP phase diagram. So once we find out that critical pressure, later we call it the quenching pressure, then we move on to the pressure quench stage, which is in the red color. So we do pressure quench. So here I want to just draw attention to the temperature is very important. So we do try quench, quickly release the pressure at the room temperature. And so far, we haven't seen any success in all the materials we tried. So all this quenched in happens in no temperature. Basically, we try 77 Kelvin and 4.2 Kelvin for the, that's the cryogenic temperature for liquid helium and the liquid nitrogen. So after we quickly release the pressure at those quenching temperature, we do a lot of measurements to confirm whether these high pressure properties are really locked in or at least partially locked in. That's for one a reason. The other reason is also we need to check how stable they are. That did they only exist only a few seconds, or they are, they can survive for a few days or even a few months. Of course, the longer the better, right? And the last stage is also the most challenging part, but that also make the pressure quench protocol more meaningful, is being able to recover the sample with the quenched in phase out from the DAC. So that can be delivered into different probes, which are accessible under at ambient conditions. So that's really the last stage and the most challenging, also most exciting part. Okay, so with that in mind, I'm going to show you three results with three systems we have been working on the past 5 to 6 years. So the reason we choose iron selenium as one of the first demonstration cases is, first, the structure is very simple. And before that, we already tested our technique on antimony and bismuth. Those are elements. So right now we feel we should move on to binary compounds. So that's one reason. And the other reason is this material also shows a very nice pressure effect, right? At ambient condition, the TC is only around 9 Kelvin, but once you add pressure, a few GPa, it boosts up to 40 Kelvin. So that's a huge enhancement. And more importantly, as I mentioned, we're thinking about you taking advantage of the energy barrier. And then the follow-up question would be, what provide those energy barrier, right? One naively thinking is those first order structural phase transition that normally come along with considerable amount of latent heat, and that can help to lock in this phase. So that's why we come to iron selenium, and this material has been continuously provide a lot of interesting physical results and insights. So we're focused on these high pressure results here. That's done early by Bob Kava and other colleagues. And so when they apply pressure, they map out the phase transitions, and the TC, as I mentioned, it can go up to 40 GPa, and it come with two structural transition from orthorhombic to tetragonal, and eventually to hexagonal, and then it lost the superconductivity. Right. So what we do is, first we carefully measure the ambient pressure pristine sample. The onset is around 9 to 10. That's consistent with everyone observed. And then we add pressure, push the onset TC to a little bit above 30 Kelvin. That make good difference between the pressure state and the ambient state from the TC point of view. And then we immerse the cell in the liquid nitrogen environment. That's why we have the 77 Kelvin here, and we quickly remove all the pressure completely, and then that's what we got. So when we warm up again, we got the red curve. So very beautifully, the TC didn't go back to 9 to 10. It retains above 20 Kelvin, even though it's not ideally like matching the blue curve, but that's kind of doubling the TC. That's already some exciting results. So we are thinking, what can we tune further, right? So here, one key parameters, as I mentioned earlier, is the quenching temperature. So in order to reduce those thermal, the thermal barrier, we're trying to lower even more to 4.2 Kelvin. So imagine that 4.2 Kelvin things are more stable, and we don't have to overcome those thermal barriers. So that could give us a larger chance to lock in the high TC phase. Actually, that's exactly what we'll observe later. So after we cooling the temperature to 4.2 Kelvin and using the new setup we have, we were able to further remove the pressure. And then we do saw the retain the TC, even though the absolute value of the resistance is not the same, but the onset TC is really close enough to the ambient, to the high pressure phase that's represented by this blue curve, and the red curve is back to ambient again, as I mentioned in above here. So after that, what we are caring about is how stable it is, right? Regarding of time and thermal stability. So that's why we do very carefully we do the measurement. So I have to mention it's really a lot of effort for our postdoc students because some of the measurements it happened is when we do the thermal cycle, we lost the contact because we don't have any pressure. So this set of data is really all measured on a single on one piece of a crystal. We're not trying to combine the results from different crystals together. So that's really a lot of effort to get these nice results. So from here, what we can tell is like once below 60 or 80 Kelvin, the onset TC is almost a constant. But as we increase the upper limit temperature higher to higher, the onset TC start to shift downwards. That's also as as we expected because of the thermodynamics. But I want to point out, like even eventually went back to 300 Kelvin, actually it didn't really retain back to the normal phase, right? Because for the normal phase, pristine example, the TC is only 9 to 10, and now we still have around 20. So that still means partially this retained state is still retained even when example warming up to 300 Kelvin. So that's very positive along this line. So we want to understand better. So here's a phase diagram summary of all the TCs. So all the black spots showing the TC under pressure and the blue squares showing the TC retained at ambient pressure by a quenching at 77 Kelvin, and the right dots showing those we do the pressure quenching at 4.2 Kelvin, and you can see the gap here. So when moving towards the lower quenching temperature, we get much higher TC. So as we mentioned, so we're really trying to understand a little bit deeper than why this could happen. So one key parameter is the energy barrier. So Yemi Ma's group was kind enough to spend a lot of effort on really figuring out the energy barrier between different crystal structures. So between the tetragonal and the orthorhombic phase, right, the energy barrier is around like 3 millieV and 6 millieV. And then the hexagonal and the tetragonal phase, which is much larger, is 0.189 that magnitude. And it's comparable to the 0.21 EV per atom for the graphite and the diamond. So that do kind of, from another, theoretical point of view, it do make sense for us to quench in this phase, even though there's still many details to map out. So this also tells us we're expect to have the hexagonal phase more stable than the tetragonal phase locked in at ambient condition. And that is surprisingly also consistent with what we saw on experiments. So I do want to point out these very interesting results here, even though it's non-superconducting. So from superconductivity point of view, it may not be that exciting. But this phase, the exciting thing is we're able to warm up all the way to room temperature, even though I'm not showing the whole curve here, but this hexagonal non-superconducting phase, once we retained by quenching at 11 GPa, was able to do the thermal cycle all the way up to room temperature and back again, and it still remains unsuperconducting. So that also demonstrates how robust this pressure quenched phase is, right? Okay, so from this set of results, there are following a few takeaway messages. So first, I think the assumption we have for structural phase transitions provide the energy barrier for the PQP success seems to be reasonable. And the PQ, the quenching pressure normally is determined by the TC we want to reach, the maximum TC. But here we want to emphasize the quenching temperature is really very important. So it's not only the pressure, also not only how fast you release, but releasing at the correct temperature really plays a very important role. And also this experiment shows us the retained effect actually can persist or partially persist even as the samples warm up to room temperature. So that's really positive news. So now we move on to the second system. So that's what we do after iron selenium. So I mean, we're still following the chain from elements to binary and to ternary. And also for this material, that also goes through a lot of few structural transitions. But to be honest, we also by accidentally discovered a few interesting points which are not planned, and that makes this experiment even more beautiful. So basically, when we start to look into this material, we're not aiming for superconductivity. So after we pressure quench the superconductivity, we're thinking whether we can look into some other properties that got enhanced under pressure. Then we use this PQP method to retain another nice properties, for example, the thermal electricity, right? So that's why we come into this compound. But the thing is, when we study the thermal electricity, conductivity is also one of the main factors. So when we trying to map out the conductivity, we find out, wow, we were able to introduce superconductivity in this system. So that's a very nice sidetrack. And we start, along that line, we still go back to focus on the superconductivity in this system. So first of all, we mapped out this TCP phase diagram, and we saw about 5 GPa turns in from non-superconductivity to non-superconducting to superconducting, and then there's a kind of a gap. It jumps above 10 GPa, reach around 8 to 9 Kelvin, and then later following by a slightly drop, and then remains almost a plateau above 25 GPa. So that being said, we do identify a few critical pressures, and the question would be, what's going on these critical pressures? That's why we go to Professor Hamley and ask for the help to look into the structures. Those are more, help us to understand the underlying mechanism. So it's a very beautiful X-ray measurements, and it was able to identify 3 different crystal structures. So below 10 GPa is rhombohedral, and between 10 and 25 GPa is monoclinic, and above 25 GPa turns into cubic. So these 3-phase and 2-phase transition critical pressure really nice well with the TCP we mapped out. So that can very well explain why we see the jump here and also the small drop when we go to even higher pressure. But the question remains, what's really going on when it changed from non-superconducting phase to superconducting phase, right? That's within the same structure, right? So at least in this below 10 GPa, we can exclude the cause for any structural transition since it's remain the same rhombohedral crystal structure. So the other way to look at it is, or we considering is electronic transitions, right? From non-superconducting to superconducting. I mean, it's also very natural connection to expect some electronic transitions going on. So it's very famous Lifshitz transitions brought up since even the early 1960s, and later on, including ourselves, there are many people on high pressure that under high pressure you could introduce this type of topological change on the Fermi surface, which correlates to the increase or decrease of density of states. Then as a result, we're tuning the superconductivity. So that's why we're trying to, we look into this perspective, whether we can get some experimental or theoretical evidence. So go back to the nice X-ray results. So when we plot in the way that C over A over the pressure, we can see a clear minimum around 4 to 5 GPa, right? That's kind of indicates, right, the possible Lifshitz transition do happen in this critical pressure, and that matches pretty well with the critical pressure that leads to change this material from non-superconducting to superconducting while still keep the same crystal structure, okay? And then also Eva and her postdoc, Busen, at that time, were also joining to study this material and really look at the Fermi surface topology. And then he mapped out with the same structural at 0 GPa, 2 GPa, 4 GPa, and 6 GPa. Eventually, we can see a difference, a very clear difference between the 4 GPa and the 6 GPa. So that further proves the idea that there's a Fermi surface topology change at this range that really makes the superconductivity emerges or kicks in. So that's very beautifully explained. So now we can really assign these 3 critical pressure with 1 electronic topological transition and 2 structural transition, right? So the next step, so this is really just finish our first step of the PQP. The next step is to do a pressure quench. So again, we talked to Eva saying, you know, from the calculation point of view, how it's really quenchable for this high pressure phase. So they were really nice enough and look into the details and do some funnel dispersion calculations. A lot of work has been done, and eventually point out it's really interesting that when we drive this phase above 10 GPa to form the monoclinic phase, and then relax the pressure, actually from the calculation point of view, it should be able to exist even at the 1 GPa, right? At the 1 GPa, there's no imaginary frequency appears here, so that kind of supporting the idea this phase is possible to you really going back to much lower pressure, okay, which originally need at least 10 GPa to form. So that's very, you know, that's very nice. So so we after identify all these, like we put out these, right, 3 structures. So if right now allow me to, you know, ask you, if you are going to do the quench, which range are you going to choose? So honestly, we're betting more on the phase 2 and 3, right? Because the phase 2 and 3, we do have these very, you know, clear structural transitions. So that give us, you know, a higher successful rate experimentally. So we, to be honest, that's what we do. So once we first do the experiment, we're quenching at this region and then here. But later on, we think we're already doing so many experiments. Why not give a try on this region, even though there's no structural, you know, transitions? So we're not really expecting we can retain anything, but just, you know, we want to still see what's happening experimentally. So surprisingly, even though I put the order from 1, 2, 3, but when we're doing quench, as I mentioned, we do the quench from the second phase and the third phase first, and we're able to retain the superconductivity. So that lines up with the hypothesis that the structural transition really helps to create the energy barrier that lock in the high pressure, high TC phase. But the more exciting thing is actually for the first phase, there's no structural transition. There is a possible electronic transition, but still we're able to retain this high pressure phase at the ambient condition. So that's really surprising, but also interesting to us, right? And for this sample, something we do further on is we spend a lot of effort to recover the sample. Because I know one of the reasons when we present our pressure quench work, people often use, you know, challenge or, you know, from a very good view, in case we do some, you know, fake experiments, that the question asked is in this way, like when you really quench the pressure at low temperature, did you really release all the pressure, or actually there are some pressure still locked in one or another, but you are not able to measure them or telling them? So one clear cut is you just recover the sample from the dynamic cell. If the TC is still there, I think it's a very strong proof that we're not trying to hold the 8 GPa pressure, right? That would be too crazy to be true. So BST has been one of the first samples we're able to recover from the DAC and measure it in the squid. That also shows superconductivity, even though the signal is very weak, that due to the extremely small amount of the sample, very thin layer, and also that's the larger piece we're able to retain at that moment. So overall, it's a very exciting result. So we were able to retain from pressure quenching from all these 3 different phases, and it's proved to be bulk effect, and it can even warm up to room temperature. So another exciting thing here I want to point out is something unexpectedly happened is when we're talking about pressure quenching phase, what we expect, the ideal case, the most nice case would be we retain a TC that can as high as we created under pressure. But what happened is even better. So when we pressure quench in this phase, we got a TC that was higher than any of the TC that created under pressure. So that basically provides that PQTP is not only approach, right, to catch those high pressure, high TC phase, but also give a chance to even discover some new phase that never exist, either at ambient condition originally or under pressure. So that's a very interesting thing. So here we further, right, proves that the PQP success do need structural phase transition for some case, but don't have to depend on structural phase transition. So that really broadening the, you know, the material base for us to use this, to apply this technique. And since we're able to recover the sample and then measure in the squid, we now are more confident to say this pressure quench effect can be bulk. Maybe in some case, I cannot guarantee that every time it's in bulk, but at least this is a very strong example that's showing it could be in bulk, right, in nature, because from non-superconducting and then to superconducting above 40%, that's a very nice evidence there. So the other thing is regarding about how robust it is. It could warm up to room temperature and cooling back, the TC still persists, and also the lifetime. So for the BST, it's extraordinarily long. So for this one, is so far the only example that we recovered from DAC and could stable there, the room temperature condition for a few months. And then we measure again, the superconductivity is still there. So lastly, as I point out, PQP can also generate new states. So that's all these we learned from the BST. So that's been one of our favorite experiments on the PQP. Okay, so lastly, of course, I want to talk about our recent breakthrough, which really set the new world record ambient pressure, 151 Kelvin in the mercury compound. So this, as I mentioned much earlier, the ambient pressure superconductivity record is again on this compound back to 1933, 173 Kelvin. So, but now we're able to break it. So it's really exciting results. So brief review of what happened in the past, right? In the right after the compound being discovered by the Sweden group, and Paul Chu and the colleagues at the time, they quickly used the high pressure technique to look into whether the TC can be further enhanced. And indeed it is. They pushed the TC above 150 Kelvin back to 1993. And then there's a few, the curves under pressure, at that time also is not that sharp, but at least it gives a very nice indication that onset TC is above 150 Kelvin. And the same year, another group, I think, is from France, and they also, saw pretty much the same onset TC, going up above 150 Kelvin, and it's very exciting. So that's the record at that time. And also back to 1994, in collaboration with David Mao's group, Paul Chu, and they further pushed the TC up to 164 Kelvin. And that was the record until the hydride kicks in, right? So now we're going back to this material again, the cuprates mercury 1223. So we're trying to, first of all, reproduce the TC under pressure. So honestly, we were not that lucky to hit 164, but we were able to, right, at least getting above 150, close to 160. So we're trying to quench, of course, from those high TC we reached under high pressure. So all those arrows pointing at other points, we applied pressure quench later on, right? So here is a quick summary of some of the experiments. We did more than 60, 70 measurements so far, and the successful rate is pretty high, so around 60 to 70%. And which including sometimes we quench the diamonds break, leads broken, those cases. So the highest TC we retain so far is 151 Kelvin, as mentioned here. So just to summarize, right, we quench in different pressures, and once we quench them at 4.2, we get retained temperature around above 145, and the highest we saw is 151. So that's from TC point of view, that's really very exciting. But of course, we were able to recover the example and also measure magnetization measurements and prove this effect is also bulk in nature. So after that, I think we were, at least for us, we're pretty convinced that this technique works for retaining the high pressure, enhance the TC back to ambient. But more fundamentally, there are some questions that leads more other probes to work on it together to answer, such as why does the TC increase so much under pressure, which actually has nothing to do with pressure quench, right? So under pressure, why mercury can reach such high TC? Of course, and then the second question follow up that's related to pressure quenching is why pressure quenching can retain this ambient pressure of the pressure enhanced TC. And then another follow-up question would be, what really matters for the long-term stability of the pressure quench phase? And how can we further increase the lifetime of this metastable pressure quench state? I think these are all very valid questions, but difficult to answer. So we start to look into more like microstructurally. So some hypothesis we have is whether it's still have some structure transition that people haven't really paid attention to, or some structural transition only happens during pressure quenching. That's possible. And when we do a few runs synchrotron X-ray, and also in collaboration with Teams group, and we were come to a conclusion that indeed there's no structural transition, right? Either under high pressure or during pressure quench. Then we move on to, how about the next parameter? So we know even though there's no structural transition occurs, our next parameter must be changing under pressure, whether we're retaining those next parameter. But again, okay, let me just quickly also, we have the DFT calculation proves that the phase was pretty stable all the way up to 50 GPa. And here's what I mentioned. So since we didn't observe any structural transitions, we move on to the next parameters. So those two stars, the blue star and the green star, showing the last parameter that after pressure quench. And again, it's very close to the ambient, the pristine examples. So that means we cannot say it's because of we're retaining the next parameter that created under pressure. So then we're looking to even more minor or subtle things like whether there are defects, whether there are domain size change. And the one very positive phenomenon we saw when we look into those, the shapes of this X-ray, we can tell it is along the azimuth direction. You can see those kind of the shape was longer in that direction. So that's an indication of the strain, and also possibly the domain were broken into smaller pieces, right? That's one of the the hypothesis here. So another thing doing by Dr. Chen and his student here at UH, were able to see some dislocations through the TEM and image. Again, it's a very challenging experiments. Sometimes we have to do many pressure quench to prepare a good enough sample to show this image that has high resolution enough to calculate the dislocation densities. So right now we're on the stage of mapping different locations. How does the dislocation density change? But one sentence summary is there is a clear indication that the dislocation density increases a lot after the pressure quench. So it may sound a little bit weird. So because normally for superconductivity, talk about disorder, defects, dislocations, they're not really in favor of superconductivity. So here we want to break up these two questions I mentioned earlier. The reason that help to enhance the TC may not be the reason that help to retain the enhanced TC. In extremely case, it could be even a factor that's not in favor of TC enhancement, but now plays an important role to retain this structure-wise or property-wise that favors higher TC. So that's why we come into these defects. We're trying to look into more experimental evidence. Of course, we also we have colleagues at the UH to calculate the density of the states. Also shows that above 10 GPa, we do see an electronic transition similar to what happened at the BST case. So that provides another source that may contribute to the energy barrier. And lastly, recently, we're also in collaboration with Chongju's group in Washington University at St. Louis. So they have those nice quantum sensor used in MV technique. The importance is it gives us a very nice tool that can really mapping the inhomogeneity and the TC distribution before and after the pressure quenching. Because it's intrinsically, when you're under pressure, the pressure medium we use is not super homogeneous. So we would imagine even under pressure, the TC distribution on the sample is not going to be that ideally homogeneous, not to mention after this very, ruptured pressure quench. Another very exciting thing for his capabilities, they can also map out the strain on the surface. So eventually we're looking at coupling the strain map and the TC map, or even the X-ray, the structure map on the same, on the same picture that could give a lot of useful informations. So with that, I would like to stop here. So I think based on our recent results we got on pressure quenching high TC superconductors, we proved that the pressure quench is a unique and a nice approach for us to really get pressure generated metastable phase at ambient condition. And they also go beyond the materials that has those conventional first order phase transitions. So you can try with different basically trying a broad range of quantum materials. And lastly, we also saw the chance to create new emergent states by the pressure quench. And even though I'm talking about superconductivity, but I just want to mention this is really can be broadly used for other materials, not only for superconductors. So with that, I would like to thank everyone's attention and I'm ready for questions.
Thanks very much, Lingzi, for a very nice talk, a great review of this technique and some of the challenges and roadmap for the future. So the talk is now open for questions or comments. Simply unmute yourself, put your comment in the chat, or raise your hand. Go ahead, Clayton.
Great talk. I'd
Thank
be
you.
interested in learning if you guys have done any more characterization on the PQ-induced phase in BST since we published that work last year.
Not yet. I think that's the one. So one reason we haven't put down priorities because we are kind of putting a lot of attention on the mercury compound. But honestly, recently we find out maybe BST is a more suitable for material for looking at the mechanism for this PQP. So the short answer is we haven't. And if you are interested, we're more than happy to continue our collaboration along that line. Yeah. Because I mean, BST really shows a very robust stability. So that gives the chance to do many experiments.
That's right. It's a wonderful material, a multifunctional material. Okay,
Yeah.
Alec, go ahead.
Hi. Yeah, no, great talk. It was very interesting. I was wondering about the mercury cuprate.
Yeah.
Because if these are recoverable, I was just wondering how much you've really pushed the ambient pressure characterization, especially the like the ones that show a much higher TC. If there is any kind of Lifshitz transition, are you able to? I know it'd be really hard, but even RPES or something.
Okay, you hit the point exactly. Actually, we have the visitor visiting us yesterday. He just left today. So
Oh.
So Long Yang at University of Chicago, they're doing
Yeah.
those the nice nano RPES, so
Yeah.
that they were able to to handle those 20 or even 30 micrometer size sample.
Yeah. Okay.
But the challenge again is how to have a nice surface and the direction. But now they fortunately they have some beam time and we're preparing the samples with them. So
Okay.
we'll see.
And one
Yes.
thing I just want to point out, because I'm aware of one paper that actually does show something similar to that increase, decrease, and an increase in a mercury cuprate.
That's
And
interesting. Yeah.
I think I can send it to you, but it does occur right around 10 GPa.
I see.
It's very similar. And it's only in very hydrostatic compression.
Very hydrostatic or non-hydrostatic?
Very hydrostatic. Yeah,
very
I can
hydrostatic.
send. Yeah, I can talk to you about later offline. I can just send you the paper,
Sure.
but
Sure.
it's a Japanese group that actually demonstrated uniaxial compression doesn't show this. Hydrostatic up
Show
down
this.
up
Okay.
in a mercury cuprate.
I see. That's interesting. Yeah.
I'll send it to you.
Sure. Thanks.
Yeah. Mehmet, would you like to make a comment, or should I read your comment in the chat?
Sure, I can verbally ask. Thank you very much for the excellent talk. I was wondering if you had more comments on hydrides specifically when it comes to pressure quenching.
I think I think many colleagues told us they won't believe the hydrides will be quenched in, because I mean they won't imagine those bonds can still exist at ambient condition. But I think nonetheless we're still going to try. That's my honest answer. We're still going to try, but maybe we're thinking we may not just one step from over 100 GPa to 0. We're thinking maybe first quench to 50 and then a few steps going there.
Right.
That's what we're trying to
Yeah,
do.
Yeah, that makes sense. So are there ongoing experiments?
Yes.
Okay,
yes.
Good to know. Thank you.
Yes.
May I ask a question?
Yes, go ahead, Laszlo.
Oh, sure.
Yes, so Laszlo Foro from Notre Dame. Langzi, it's great talk and
Thank
congratulations
you.
for the data. It's absolutely great.
Thank you.
So concerning the pressure dependence of the cuprates in the
Yes.
mercury and non-mercury,
Yes.
does it give you some idea about the mechanism of the high TC?
That's yeah, that
It's a tough,
that's a
tough,
hard
tough
question.
question.
Honestly, no, not yet. That's really what we're trying to do. I mean, with the hope, right? I think right now, if we really can quench in the high pressure phase, we are imagining we could do more measurements at ambient condition that can help us to understand. But still, we're not there yet. That's the honest answer. But with the hope, I can only say with the hope. Yes.
So
But
on
if
that
you have any suggestions on the direction we should look at, we're more than happy to learn from you. If there are, certain direction we think we should be a little bit more focused, or
So on that point, you showed some calculations. So those were standard DFT calculations?
yeah, I think that's, you mean like this one?
Right. Yes.
Yeah. Yes.
So you think maybe
I'm
DFT is sufficient to capture the physics here or not?
I think it gives some insights on the possible electronic structure transition, but I know which the other one is really challenged. So I'm thinking if some serious friend, they can simulate the quenching the process, that would give a more, but I talked to some, but I know that's very, very challenging. So if that's possibly made, and that could be precise some insightful information. But we do have some colleagues in Cambridge, they're working on this and get some nice information, but we're not ready to share yet. But I think hopefully soon. Yes.
Right. Okay, thanks. Ranga, do you have a question?
Oh, yes. Hi, Quantum. How are you? It's very nice
Hi, how are
talk.
you? How are you? Yes.
I have a couple of technical questions. So,
Sure.
especially the 150 1 Kelvin experiment. Were you monitoring the pressure while you were doing the thermal cycling in situ?
No, that's the quick answer. And I know that's always been a concern that during this thermal cycle, you could build up a lot of pressures. Yes, I think that the way we do is definitely when we raise up to room temperature, we bring the cell to measure the residual pressure. Normally it's below 0.1 or 0.2 GPa. And I wouldn't imagine during the thermal cycle being that, loose the screws can build up 5 or above. But if you think, a few GPa in extreme cases is possible. But yes, I think the more clear cut would be we have a cell that can do in situ pressure measurements that tell you at each temperature how does the pressure change. That would be more convincing. I think you're trying to hit
Yeah.
that point.
What's the qubit size you were using on this experiment?
It depends. So for the most recent mercury, we're doing 300. Since we only go below 50 GPa. So yeah.
Because we do, especially if you use 300, that's a sizable QLED. So when you do thermal cycling, there's a significant changing in pressure. Even though you completely remove your screws, it doesn't actually see the 0 GPa. I think, as you mentioned, the clear way to kind of like understand this is to really take out the sample out of your diamond anvil cell and measure it outside. And that way, any questions about the pressure being is still, because it's I did see because some of these in the paper, in one of the supplementary paper, I think you did show a figure. You were doing the CFC, I believe, on using the spin,
I think
right?
the BST we do, that one we really recovered.
So the mercury one you didn't.
We recovered, but the sample is to us, it's very challenging to put the leads on it again on the recovered sample.
Yeah, the slide 47, I think, as in that's the one, right? If you go to the slide 47.
Slide 47, this one?
46
one?
probably. Yeah.
This
so
one?
this is the one, right?
Yeah.
So this is the one you recover 66 micron out of the diamond cell. So because this seems to me it looks like about 130, 135 Kelvin TC. So I think because if you look at your background level, because now you're taking out from your sample When you do the resistivity, you have your pressure medium. What were you using? You're using, what is your insulation layer?
A sodium chloride. Sodium chloride.
And plus you have an insulation layer to protect your leads from this. So you're picking up all of these, right?
Correct.
So don't know how much background is you're contributing. So the zero level, the fluctuation, what I see, I think probably had to kind of like get a bit of understanding of the background. But it's very clear about 134 Kelvin, I think. Do you have the FC on this one too?
Yeah, that's you know what we're doing right now. So for this one, I think when I do want to point out, right? So when we recover the sample, there's a lot. I have two concerns. One is even when we recover the sample from the pressure cell, there's a lot of things going on. Sometimes even though you retained, you imagine you're trying to poke it and doing the kind of messed up the quenching state. So what we're working on right now is really with the cells, with the sample inside the cell, we can map the TC and map the pressure. That's another way of what you are asking for, the in situ pressure measurements and the TC. Yes, that's what we're doing.
Yeah, that will help us to really better understand the system.
Exactly. I agree. I agree with that. Yeah.
All right. Thank you. Thank you very much.
Sure.
Thanks.
Thank you.
So as a follow-up, and we're doing more and more measurements where we not only monitor the pressure as a function of temperature and also, say, resistivity, but also the structure. So that capability now exists. So we've been doing that. We did that with BST in this follow-up paper that we just did with you. Done it for germanium and for more materials. So we can do all of it on the beamline, measure pressure, measure structure, and transport properties.
Yes. That is one thing I do want to ask you. So I think that recently, like Loma Yalder group, right? They're doing the licolis. That's what they're trying to do the NV, and they were also able to map out the stoichiometry at the beamline. Is that something you can also, do it? Or I don't know the details.
You can constrain that from the X-ray mapping. So that's an additional capability that you now have with sort of micron scale resolution. If you can correlate the structural changes or the structural differences in the map with the stoichiometry, then you have that constraint. You're right.
I see. But I think one challenge for the mercury is we didn't see any structural change, right? So that's a little bit, challenge on.
Yeah, that's very interesting.
But that's also interesting. Interesting.
Right. Well, thank you very much for an excellent talk. There was clearly a lot of interest, and congratulations on this work so far.
Thank you.
Okay, thank you all for joining us.